It's a great honor to give the Earl Ingerson lecture, and particularly it's very special to me because I just checked the list, the lectures, and my PhD advisor, Roberta Ranick, delivered exactly the same lecture about 20 years ago.
Not on potassium, I see.
Yeah, that's right. So as Dominic mentioned, Earl Ingerson has done a lot of service to the Geochemistry Society, the general geochemical community, and he's the founder and the first president of the Geochemical Society, and he helped to found the official journal of GCA. And he is also the first president of the International Association of Geochemistry and Cosmochemistry. Now we call it International Association of Geochemistry. He helped to found the official journal, Applied Geochemistry. So it's very appropriate today we gather together here to celebrate another great man. That's Bill McDonough. Bill is a great geochemist. So from whatever metrics you like to measure a great man, Bill is on the list. I just show you one thing here. This is his citation score. I got about a few weeks ago, so it's probably more than this. You can check now. So it's really truly amazing. Just take a look. But I think what's more amazing about Bill is he's also an entire geochemistry advocate. Well, one time he was drunk. I don't know if he's drunk or not. He told me he liked geochemistry when he was in high school. But many of you, I'm pretty sure, have read some papers published by Bill. This is a great for Bill is he wrote very insightful yet very accessible papers. I just list a few here for you to check, and I assume you are familiar with it. So this is about the continental lithosphere, and this one is about something about basalts. Quite a few know, probably. Then this one about the composition of the Earth, and this one is about the core. So as you can see, and but these are something I feel like everybody knows. There's another thing a few of you probably know it, is Bill is a really extraordinary mentor. So he spent a lot of time with his students, postdocs, junior faculties. And sometimes we don't like that because he spent even more time with people outside of his group. So last night at the icebreaker, someone asked me, hey, have you seen Bill? I said, no, but I know where he is. So just go where the most young people are centered. He will be there. So that's Bill. There's a saying, is that the best teachers are those who show you where to look, but don't tell you what to see. I feel like this is exactly the philosophy Bill has been using to mentor us. But sometimes this method doesn't work. Like in some cases, I'm not going to mention the name, but you can see it. So if this doesn't work, then Bill will change his method, and then will meticulously shape the students, put them back on track, especially for students who fail their prelim exams. Okay, that's not me. Okay, so so today, Bill's students, postdocs, and colleagues and friends, we get together here to celebrate his great achievement. And I like to dedicate my talk to Bill. And before I talk about potassium isotopes, I like to acknowledge my collaborators. As you can see from the list, many of them are my students and postdocs and then colleagues. And as you will see too, the talk mainly from their work. So you may ask, why potassium? I know Bill will ask if I tell him I'm going to work on potassium. So the answer is very simple. Because it's a great tracer of planets from the inside out. Well, quite a few of you probably are familiar with this work by Ross Taylor. And this work was published more than half a century ago. And they used potassium rubidium ratio to figure out the petrogenesis of igneous rocks. Well, later, Bill White and Bill Bryan, they used potassium, a bunch of other trace elements, and strontium isotopes to study the famous basalts. Well, here comes the main mafia. So from Johann, L. Hoffman, then White, Stewart, and Ito. So they use potassium, uranium, thorium to study the moths and the mantle. Okay, I don't know that part of the story. Okay, so here comes young Bill at that time. So he worked with Shensu San, Ted Ringwood, Emil Yaguz, and Al Hoffman. And Bill used potassium, rubidium, cesium to study the evolution of the Earth and the Moon. Well, he doesn't stop there. So here with another guy called Rick Arvelo, who is here. So they use potassium-uranium ratio of oceanic salts to study the mantle composition, structure, and the thermal evolution. Well, I thought they should stop, but no. So here I show you another paper done in collaboration with Alex Corner et al. And they try to answer one question: how much potassium is in the Earth's core? I think it's still debated today. But anyway, I just give you a few flavors. You see, potassium is very, very powerful, and you can use it as a great tracer to trace a lot of processes. Well, then I know you will ask, well, potassium is so useful. Why bother for potassium isotopes? Well, I'm old enough now, I can ask you, why not? Okay, but before we start the arguments, I want to make sure we talk about the same thing. So as you know, potassium has 3 isotopes, 39, 40, and 41. The 40 is radioactive, decays to argon and calcium. So that's the systems a lot of people are familiar with. But what I'm not talking about today is the 39 and 41, the 2 stable potassium isotopes. So they have about 5% mass difference, and that can potentially lead to large stable isotope fractionation. So to come back to the answers, why potassium isotopes? Actually, potassium is one of the first isotope systems studied for geological and medical sciences. So this is a paper I just got from the online library. So Keith Brewer measured potassium isotopes in minerals and plant sources almost 90 years ago. Then slightly later, Taylor and Urey, they studied potassium, lithium isotope fractionation during ion exchange with zeolites. Well, then Keith Brewer's group, they here studied how potassium isotopes can be potentially used as a tracer for cancers. So this is really amazing. But nonetheless, the stable potassium isotope geochemistry hasn't been widely used to study geological processes until recently. But I have to mention one work done by Humayun and Clayton in Chicago. They developed a method to measure potassium isotopes at fairly high precision, and they measured extraterrestrial samples. From there, they talk about the volatile depletion history of the early solar systems. Unfortunately, at that time, the precision is not high enough, so we cannot see the variations in terrestrial samples. Then a few years ago, a bunch of groups, including ourselves, developed the high-precision potassium isotope analysis, and we can clearly tell the same samples shown 30 years ago, they have very different composition today. So since then, a lot of things have been done for potassium isotope geochemistry, and the applications range from cosmochemistry, biological processes, to cross-mantle interactions. You already got some flavors from the talks in the morning, and please check out some posters in the afternoon. Today, I'm going to just focus on the magnetisms at the convergent plate boundaries. And particularly, I will give you 2 examples to show how powerful potassium isotope geochemistry is. The first one is I will talk about how we can use potassium isotopes to study petrogenesis of the island arcs, the Los Angeles arcs. It's a classic place where one oceanic crust collided with another one. Then my other example is the Himalayan leucogranite. It's formed during the classic continental collision. So this is the Los Angeles arc, and I assume everybody know this place. So subduction of the North American plate and the Caribbean plate from these arcs. And at the same time, the Orinoco River from the South America delivered a huge amount of sediments to the Atlantic Ocean, and these sediments are subducted down to the trench. A lot of studies have been done on this place, and they clearly show the arc lavas have very similar radiogenic and stable isotopic compositions. And I just show you one textbook example. Show you here is neodymium versus strontium isotopes, and as you can see here, the less antillate samples fall between the mobs and the subducting sediments. So there is no debate about the incorporation of sediments in the arc lavas. But however, there are huge debates about where and how the sediment was incorporated into the lavas. Well, there's one hypothesis is the sediments or its melt was added in the mantle wedge, while alternatively, people believe the sediment was added in the arc crust. And other people also think, well, fluids play an important deal in petrogenesis of these arc lavas. So what I will show you is actually the potassium isotopes can help. So we analyzed a set of samples from the Martinique Island, and the reason we choose these samples is it represents the compositional end member of the global islands. So in these strontium lead isotope diagrams, we plot the typical island arc lavas. The small green dots represent samples from the less antillates. The big ones represent our samples for potassium isotope analysis. And more interesting for this arc is we know the composition of the subducting sediments. So compared to the mantle, well, seawater is really heavy. Compared to the mantle, the potassium isotope composition of the subducting sediments are really light. So in other words, you are injecting something very different compared to the mantle. So here are our results. Well, first, you will see compared to the mantle here, these are the arc lavas, the blue dots. They are heavier and also lighter compared to the mantle. But nonetheless, compared to the subducting sediments here, they are heavier and they move towards the subducting sediments. And these are representing the continental sediments. So remember, I want to answer two questions, right? So where and how the sediments were incorporated. To answer the first question, so where, we check the hypothesis about mixing in the arc crust. So to do that, here we plot potassium isotopes with radiogenic isotopes. And I show you the lead isotope here and the potassium isotopes here. So the two end member mixing, all the AFC processes doesn't explain the data well. Because in order to explain the potassium isotopic variation, we need up to 90% of sedimentary inputs. That's way too much. And also, this doesn't agree well with the previous studies of radiogenic isotopes. So how about subduction in the arc mantle? So again, we use the same plots, potassium versus radiogenic isotopes, lead, strontium, neodymium. And as you can see here, the bimodal mixing is much, much better. And also, in order to explain this data, we only need less than 5% sedimentary inputs. And that's very manageable. And moreover, we found those three heavy samples here, and their isotopic compositions can be explained by the addition of the heavy slab fluids. So I think we answered the first question, where the sediments were added. So it's in the mantle wedge. Then the second question is how. Well, to answer this one, we plot potassium isotopes versus thorium-neodymium ratio. So as you know, thorium is more incompatible than neodymium. So during partial melting, this ratio will increase in the melt compared to the original melt. So as you can see here, if you do a bimodal mixing, you will see this mixing line with the sedimentary melt is much better than this one. So that means the sedimentary was added in a form of melt. So, in other words, the potassium isotopes help us to answer the questions where and how the sediment was incorporated into the arc lavas. Well, that's the sedimentary melt in the mantle wedge. And also, it also helps us to tell that fluids also contributed to some of the arc lavas. So this is my first example to show you how potassium isotopes can be used to study island arcs. There are a lot of other studies ongoing and published recently. If you are interested in this topic, you can check them out. The other one I want to talk about is totally different. It's on the Himalayan local granites. Well, if you are interested in granites, you will know Himalaya local granites is one of the classic and well-studied local granites worldwide. And it mainly exists along two belts. So one is called the higher Himalaya belt. The other one is the Potassium Himalaya local granite belt. So this is what you see in the field. So their petrogenesis, although have been studied over 40 years, are still highly debated. Well, I'll just show you a nice picture here. This is the mountain Trumelanzo. The whole peak here is made of local granites. So the debate can be about the mechanisms to forming these local granites is, are they formed by partial melting or by fractional crystallization? Are they source rocks or sediments? In other words, are S-type granites, or the source rocks were I-type granites, then you contaminate them with a lot of sediments. Well, the different answers have very different tectonic implications, and many of you probably know this. Well, one end-member hypothesis is the channel flow hypothesis, and they suggest the anataxis led to deformation, led to the channel flow, then led to the formation of the local granites. While by contrast, the critical taper said, no, that's opposite. So you have deformation, then you have anataxis, then you have formation of the local granites. So today I will focus on the mechanisms, and especially I want to talk about how fractional crystallization can potentially modify local granites. Well, everybody knows crystallization. Well, this is something we learned from the Geo 101, and this has been well shown by Bowen about 100 years ago. So you have a mafic magma chamber, crystallization of mafic minerals because of the high density, lower viscosity. So they will sink to the bottom of the magma chamber. Then the remaining materials will evolve to more felsic. However, for high silica magmas or felsic magmas, it's quite different because we know the viscosity of magma increases with silica content. So, well, rhyolite is here, basalt is here. And furthermore, if you take a look at the density difference between felsic minerals and the magma, you will see actually their densities are quite similar. So in other words, the density difference is much smaller between mafic minerals and the basaltic magma, much bigger between the mafic minerals and the basalt magma compared to this. So both of them will make the gravitational settling difficult to do. But nonetheless, people propose the MASH model. So what they suggest is, well, you have a high degree of crystallization, then you form two zones. The crystals will completion, they form a MASH zone. Then the remaining thing, small pockets of the melts. So if the small pockets melts erupted, they will form rhyolites. Well, if they crystallize, then that's your local granites. Then for the majority of the MASH, they crystallize, they form the granitoid plutons. They represent the cumulates. Well, if this is the case, then potassium isotope can help to tell. Why? Because our study suggests that while during mafic magmatic differentiation, there is no isotope fractionation. As you can see here, so the potassium isotope doesn't change with magnesium concentration from like a greater than 25% to less than 5%. So in other words, crystallization of olivine pyroxene will not modify the potassium isotopic composition of the basaltic magma. But for felsic magmas, what we found is we analyzed some coexisting minerals from granites, and we found there's a huge isotopic variations. And more importantly, we found a compositional control of potassium isotope fractionation in pelagic clays. So here on the y-axis, we show you the isotopic difference between pelagic clays and the K-feldspar, while the x-axis to show you the pelagic clays composition. As you can see here, you basically have pure pelagic clays and the pure K-feldspar. The fractionation between the coexisting minerals is over 2 per mil. That's really huge because our analytical uncertainty is about 0.05, 0.06 per mil. So why this happen? Why this is important? Because pelagic clays is one of the first phase to crystallize in felsic magma. So if you have a magma like this with this potassium isotopic composition in the beginning, with increasing of crystallization, then the cumulates, the pelagic cumulates, their composition will decrease like this, and correspondingly, the melt composition will be like this. So in other words, you expect the cumulates are heavier and the melts are lighter. Well, to test this, we analyzed quite a lot of representative leucogarnites from the Tibet, Himalaya area. And we have about 36 2-mica leucogarnites. Then we have 18 musquite leucogarnites. So both of my leucogarnites, the only difference lies in the difference in the mafic minerals. Well, for the top one, you have biotite. For the bottom one, you have tourmaline or garnet. Well, now I show you the potassium compositions. So this is the average composition of the upper crust, and this represents the random literature granitoid samples. So for our 2-mica leucogranite samples, we found compared to the crust, their compositions display much larger variation, but overall they're heavier. And they also have very high silica content. Well, then these are the musquite leucogarnites. Well, by contrast, these blue dots, triangles, compared to the upper mantle, their isotopic composition are lighter, and they have even higher silica content. Well, then when we plot the potassium isotopes to the trace elements, strontium, rubidium, strontium, uranium anomalies, and as you can see here, especially for these samples, we see a nice correlations. The potassium isotopic composition of these leucogarnites increase with strontium concentration and uranium anomaly, but decrease with rubidium strontium ratio. So clearly indicate of plagioclase separation. Then for these samples, they probably represent the plagioclase accumulation. It's very difficult to tell cumulate structures in granite, as you know. So, but more or less, if what we said here is right, then we should see some kind of correlation like this. You should expect potassium isotopic composition should more or less vary as a function of the plagioclase modal abundance. And that's what we see here. So for these heavy samples, indeed, they have much more plagioclase compared to the more or less light ones. Well, if indeed the samples are formed by crystallization, then we can model it. So this is what we did. So we plot potassium versus rubidium strontium ratio. Then we modeled the crystallization. So we assume the parental melts have more or less the same composition as the upper crust. Then from there, we use the rhyolite melts to model the crystal faces. We don't have any fractionation factor for the minerals and granitic melts yet, but more or less we just use the difference between mineral versus autoclase, because anyway, most potassium will be in the autoclase. So these are our results. As you can see here, in order to produce these really light isotopic compositions, we need about 80% of crystallization. And to produce this very heavy accumulates, they have to form earlier. Like the crystallization degree is about 10%. So from here, it clearly shows fractional crystallization plays a very important role in the formation of the leucogarnites. So I'm not going to talk about too much about Himalaya leucogarnites. So if you are interested in this, a few months later, the Elements magazine will publish a special issue about Himalaya leucogarnites. In that issue, we invite experts from all over the world to talk about the petrogenesis of the Himalayan leucogarnites. So to conclude, I hope I show you potassium isotope geochemistry is a great tracer of magmatisms. And for the less antlerless lavas, the sediment melt was added in the subarctic mantle, and the fluids also contributed to its petrogenesis. Then for the Himalaya leucogarnites, crystallization plays a very important role. Finally, I want to say congratulations, Bill, for a great contribution to the geochemistry community. And personally, I really appreciate your great mentorship. I will stop here and take any questions. Thank you.
Questions, please.
Don't feel pressure to ask questions.
Sure, go ahead. Would you expect fractionation between the core and the mantle with respect to potassium isotopes?
I think in theory, yes. But people did, not my group, Kun Wang's group from Washington University in St. Louis, they analyzed quite a lot of extraterrestrial materials. From their conclusion, there's no potassium in the core. Sorry, Bill. So
I don't want it in the core.
okay, yeah, but but in theory, yes, you should expect potassium isotope fractionation between metal and silicates.
So for the Himalayan leucogranites, I understand your main conclusion about crystal fractionation, but I'm still wondering, is it taper or is it channel flow?
I don't want to talk about it.
I didn't get that out of it.
No, there are a lot of people will be mad at me. So, well, depending on who you talk to. It's really depending on who you talk to. We cannot. Well, I don't want to make the conclusion basically. But what I will, what I said here is, you cannot use leucogranite as index of anataxis. So in other words, people use leucogranite as the index of partial melting. Then from there they talk about partial melting. Then they talk about decompression. Then they talk about the crustal flow. But the leucogranites provide the most important constraints. What we said here is not all leucogranites are highly fractionated, but a majority of them are highly fractionated. Then you need to check your evidence again. But our data cannot directly support the critical taper theory. But at least we cast doubt about the crustal flow model. Yeah, that's what I will see. Yeah, but I know like a lot of people a lot of debates about it. So yeah, go ahead.
Hi. Could you go into a little bit more detail about some of the processes that cause potassium isotopes to fractionate?
So why they are fractionated?
Yeah.
Okay. So again, so this is based on our own study. We think the potassium bonding environment in pelagic clays and K-feldspar is different. And in the pelagic clays, the bond is shorter and it's stronger, so that's why it favors the heavy potassium isotopes. While in K-feldspar it favors the light potassium isotopes. But I did talk to some modelers about stable isotope fractionation. They feel like the bonding environment is not so different. There's no way you can produce 2 per mil fractionation. But as always, I talk to modelers. I trust you guys, but I trust my data more than your theory. So I tell you, it's not my problem, it's your problem. So, yeah.
Sorry, could it potentially be something else like aqueous alteration that could fractionate?
In our cases, okay. So if you talk about fluid, right? I had a small fluid, then raw minerals. Yes, that can potentially affect potassium isotopes. But for all our samples, we pick up the really fresh minerals because we don't need a lot for K-feldspar. For pelagic clays, we got it's very easy to separate. So we separate. So they're really pure. So I don't see any alteration.
Okay. This was a really nice talk. Thank you.
Thank you.
Right, we need to move on to the next talk. Let's thank Fang-Zhen again. And the next speaker is Fang-Zhen.